That's a date. Oh, is it blinking? I think that's because it's recording. It's got plenty of power. It's recording. I'm just trying to get the video fixed. There you go. And it's got up to that dash. Yeah. Yeah. Have you guys attempted the homework 6 that was due today? Did it go fine? Not too bad. Just get a kind of weird eigenvector in the first problem, and then have to realize a certain angle identity from the result. So what was the first problem? Remind me. The n hat dot sigma vector finding the eigenvalues vectors. But it worked out well. Yeah. Everyone else? Worked. Yeah. Also, seven. So Friday's lecture will not happen because it's a fall break. So usually we have 2 lectures for a homework. So the next homework will be due on 1 week from Friday. So that was a wake up. So that was 17. Right. Midterm 2. It's 2 weeks from then. We want to start a new topic today, basically Fourier transforms. That's what we want to do, but we want to do it in a way we can connect it with the idea of vectors. Like we have done vector space, and there were some ideas we used to find components of a vector. We want to do the same thing in the case of Fourier transform also. Basic idea is that any vector in 2 dimensions can be written in terms of unit vectors I hat and j hat. Similarly, any function can be written in terms of Fourier eigenfunctions. So that's the idea we want to build. So let's remind ourselves of the vectors, right? So in how do we recall vector space? Like just vectors. So usually let's think of 2 dimensions. We have 2 unit vector. So we have a completeness relation. And that tells us that basically it's a collection of eigenvectors. So that is E1, E1 plus E2, 2. If it was I hat plus j hat, this will be equal to 1. That's complete number. It's in quantum mechanics, we last week did quantum mechanics. This will be equivalent to, let's say, if it was I, let's say that if these are eigenvectors of I, so you would say I. So this is a summation, right? So there's a summation, and you would say that's the 1. Same idea. And then usually there is also an orthonormality condition or orthogonality condition. And that is that EI dotted with EJ is equal to delta J. So if it was I had a J hat, I hat multiplied by the I hat itself gives you 1. J hat multiplied by J hat gives you 1. Otherwise, it's 0. Yes, same. Scalar one. It's the same thing. You just stop writing that vector. So, okay, how about this? So you give the idea that this one, so basically you write this as E1. Yeah. And then you write this as E2. So this is E1. So instead of writing a vector, you start writing a bra and a cat. And then you say that E1 of, if there were only 2 states, usually there are more than 2, but if it was a spin state, for example, then you would say this is, so bottom is, maybe the other way, right? So this was 1, so then you would say this is E. Oh. Did I do this right? So then this is E1 plus E2, and this should be a dyadic in this form, or you just write 1 in quantum mechanics, it's common to write this one, but it is in this form, this is equal to 1. So it's kind of a different notation or different. It's just a matter of notation. So maybe this is equal to say, okay. It is equal in a sense, but it's a notation. It's reasonable, so good point. Okay. Now, what do we do with this? Remember, in vector spaces, so you take any vector, so a projection or vectors, right? Yeah. So if you have a vector A, any vector can be uniquely represented in terms of its X and Y components or in terms of projections in these components. So how do we see that? You will say, I want to project it. So you begin by saying that A is exactly equal to A times 1. Right. That is how you would say. And it is good to now that we have introduced this quantum mechanical operation, you will say instead of A, you will say any state. Dirac says that any state is just written as an empty state. That's Dirac's notation. So that's any vector A. You will multiply it in terms of a unit vector. So you would say this is equal to, I want to project it, correct? I think so. So maybe let's not do it this way. So let's do it this way. But So this is a completeness, so this is 1, right? So I'll just multiply by 1. And here you would say A times E1 plus E2, correct? Here you would say this is one good. From this step to the next step, the only thing I'm going to do is change the parentheses. Here, this is the parenthesis is collecting the 1, but now I really project this into individual vectors. This is E1 times E1 plus A dotted with E2 and the direction of E2, right? Earlier we said this is being multiplied by 1, but now the language is that these are projections in the direction of E1. That I will define as my components. This will be A1 times E1 plus A2 times E2. Here the notation is where A dotted with E1 is equal to A1 and A dotted with E2 is equal to A2. Right? So in general, that's the idea of completeness relation, that any vector can be written in terms of its components and uniquely. It's not just it can be written, it's a unique way of representing. What do you do in quantum mechanics? The same idea. This is an arbitrary state. And now change the parentheses to collect the projections. So this is the projection of the state along the eigenfunction E1 times 1 plus projected along E2 times E2. You can give it a name of, let's say this is C1 times where C1 is equal to projection along 1, C2, in general, these need not be 2. This could be a whole summation. This could be a whole summation, right? That could be, this could be an n-dimensional space, and this could be an infinite dimensional space. In the two cases, I think, Payne, you pointed out what's the difference between the two. There is one slight difference, that if you're doing in 2-dimensional space, these are real coefficient. This will come out to be real. And in complex, in quantum mechanics, typically these are complex. So that's the only significant difference that comes in. Okay. So that's the basic idea. And there was also this, I think no, this is fine, right? Yeah, we didn't use orthogonality at all in this, right? I don't think so. Yeah, so this is a projection of A. Now, we want to do the same thing for Fourier transform. So this will be called Fourier eigenfunctions. Notice what the most important piece was this, right? That there has to be a completeness relation, and once this is there, you multiply by 1, and you have to make sure that these are the components and they should come out unique. For every vector, there are two components tells you what that vector is, or these two components tells you what that vector is as a one-to-one mapping onto that. Same thing in Fourier space, except that instead of a vector, we are now talking about functions. But first we should think of what are these eigenfunctions, correct? So let's say m is going to be equal to 0 plus or minus 1 plus or minus 2 and so on. So basically they are integers all the way running from minus infinity to plus infinity. There is another parameter phi, which is an angle. It is less than 2 pi and greater than or equal to 0. And the eigenfunctions themselves will be, e raised to I m times phi. Now, similar to this, we have to say what is completeness and what is orthogonality. So completeness relation would be notice the idea here. This is a summation, right? So maybe I should write it in that form here. So this is summation, right? M going from 1 to 2 vector em. Right, that's it. That's the way you can write that. And the same idea here, but now it is going to run on infinite infinite points if you want on the discrete, all the integers minus infinity to plus infinity. These are the eigenfunctions. Instead of these vectors or instead of this Brasset cats, we want to talk in terms of the eigenfunctions will be exponential e raised to I n phi. So there are two of them. So you would say this is e raised to I m phi. The other piece, we are now not writing it as a vector, not writing it as brackets. These are actual functions. The other one will be, usually it's a complex conjugate. So it is minus I m, but now phi goes to phi prime. So these are the two indices if you want. There are two vectors here, right? So m is summed over. There are two free indices. There are two vectors in there. So that's being served by phi. Those vector indices are discrete, but this is a continuous variable. So this is a vector space. This is usually called a function space, right? Since there are continuous variables, so it's an infinite dimension. You can say this is a finite dimensional vector space. This is an infinite dimensional vector space. So that's the idea. When the components of the vectors there are infinite of them, then you say it's a function space. This is so now this is equal to, here it was 1, right? But now we have an identity matrix which has infinite dimensions, right? This is usually we say 3 by 3, 5 by 5 matrix, but now we are talking about infinite dimensional space, so it is practically an infinite dimensional identity in a sense, and that will be a delta function. This is completed. There is a one-to-one, at least thought process wise, there is a one-to-one connection between the two. Any questions on the analogy there? Okay. We need to talk about orthogonality also. Orthogonality will be, so notice here m was sum, but instead here it is the dot product between the two. So there is an orthogonality you build out of the other two vectors. So here it is phi we have to add on. Phi is a continuous variable, so we do an integral. So orthogonality would be, instead of summation, now you do integral d phi 0 to 2 pi, and this time you say it is e raised to I m phi. I'll keep the phi the same, but the index will change. This will be I n phi. What is phi? Notice the difference here. M remains the same, phi is different. In orthogonality, phi is same, but the m are different. So you're talking about if you take two independent eigenfunctions, there is an orthogonality satisfied. But what will it be? In this case, I gave it right away because it is harder to prove that, or not really hard, but it is easier to not go through that. But here it is an easy integral. How much is this integral? What is that equal to? This is a phi integral, or let's do this, right? D phi e raised to I, think of an integer n times phi. How much is that equal to? For any m can be integers. Let's say m equal to 1. How much is that? Evaluate the integral for m equal to 1. Good, 0. And why is that?
Why just do force? The signs for the 0.
Very good. That's the brute force is good enough. One way, if it is 0, it must be 0. Good. What if m was equal to 2?
It's still 0.
Still 0.
Bounds that to pi net 0.
Very good. For 2 also, what about m equal to -1? Is that clear? Basically, write this as cosine and sine. So it is oscillatory functions, they're all 0. So for all m's, it is 0. Is it always 0? Try for all integers.
Yeah. It's just a rotation around. By 2 pi numbers.
We didn't care about the m, but if any number for m is equal to 0, then going to 0 to the pi means.
So when m is equal to 0.
Very good, right? When m is equal to 0, this is 1. That's 2 pi, right? So there is an exception to this case. So this is equal. Let's put that 2 pi here. So this is equal to 0 if m is not equal to 0, but it's equal to 1 if m is equal to 0. Good. That's for this, but if I want to write it in this form, this will happen whenever m is equal to n. So this is nothing but delta mn, right? That's your orthogonality, right? This was ij, delta ij, that's your delta mn, that's the integral of it. So that's your completeness and orthogonality. And the claim is that if you have any function, you can expand this in terms of this eigenfunctions. If you have any vector, you can expand it in terms of these unit vectors. How did we do that? Just multiply it by 1. Right? We'll do the same idea here. You'll take any function, multiply it by 1. 1 is a completeness relation, right? And then find the component. So always we have to be able to find the components, right? That's our idea in Fourier space. So let me erase this part. So any functions will be f of phi, right? This is any arbitrary function of an angle that is phi, and I have to multiply by 1. 1 in this case is a delta function. So this is not, notice this is like a what is this called? Matrix product is involved, but now we have to do integral for that. So how do we introduce that 1? This is the same as not minus infinity to plus infinity, 0 to 2 pi, right? So 0 to 2 pi. d phi times f of phi prime, let's say, and delta of phi minus phi prime. What is that integral equal to? F of phi again. So instead of introducing this 1 here in this form, where notice this is a summation, right? That this dot is a summation. Instead of the summation, I am having an integral there. Right, that's a idea. But now once I have a delta function, here once I have a 1, I can replace it with the completeness. There it is a delta function. I will replace it with this whole summation there and do the same thing. So this is equal to 0 to 2 pi phi prime of phi, and delta function is summation there, and going from minus infinity to plus infinity. I can write it as phi prime at phi here, so let me write phi prime this way and e raised to minus I n phi. Oh, I think I forgot, right? There was a 2 pi here, right? So this was a 2 pi. Okay, so that's it. As we did here, we just have to reshuffle this and get the components in one form. So we keep the phi here. So this phi can come out of the integral. This cannot come out because there is an integral here. This phi is independent of this phi, right? So I can write this as take the summation all the way out, m equal to minus infinity to plus infinity, and e raised to minus I m phi. So that's done, and whatever is remaining is your 0 2 pi prime f of phi prime. And I can put that in parentheses if you want, just to emphasize that these are the components, right? These were my components there. So I'm going to call those components. So let me label them something. This will be called e raised to, I'm going from minus infinity to plus infinity, e raised to minus I. Once I have done my phi prime integral, the only thing it will depend on is m, right? Phi prime is all gone. It will only depend on m, but it will also depend on this. This is a property of this function. So we will label them as f of m, and then let's call it tilde. Where the notation is f of m tilde is equal to 0 to 2 pi prime of phi prime. These two together is what is called Fourier transformation. I have a function. These are its components, where the components themselves are given by this. Notice again a vector. So if I were to bring it down here, right, a vector can be written in terms of the eigenfunctions or eigenvectors as components times this, where the components are given in terms of the eigenvectors itself. Or this is a way to find the component of the function. And if I can do these integrals, I know the components, and these are called the Fourier components of system. So maybe the usage is Fm is equal to the Fourier components of f of y. We can do some examples, right? That is something that we can do, right? Any questions? That is a basic idea now. Yeah, but while we are here, let's do one more thing. Yeah, let me copy this down here so that I have more space. So this whole idea is that f of phi is equal. Oh, something is missing here. Hold on. Something is missing. Oh, because I think I just randomly wrote this, right? That should be 1/2 pi. Isn't it? Yeah, this. So that will give you a 1/2 pi here. 1/2 pi, I can build it in here. And then that will be 2. These are notations. Notice I didn't have to really put that. In this case, I have to put it, but I could have always absorbed that 2 pi into that function. So there is a freedom of where to put that 2 pi, whether do I want to put the 2 pi here or do I want to put it here. So the differences in literature will be, is the 2 pi here or inside this? Like I could have put my 2 pi here inside the parenthesis or outside the parenthesis. Right, so different people do it differently. Usually, how does it go? I think particle physics will do it here. General relativity people do it there, and in quantum mechanics, you divide it exactly equal. You'll write square root of 2 pi and square root of 2 pi on both sides. So different people do it differently, different textbooks do it differently, but mostly it is harmless. It's not a serious issue at all. So I was just popping this down here so that I can use that board space. M equal to minus infinity to plus infinity. Here it's minus I phi. That's that. And components itself is equal to 0 to pi. Also notice the difference here. One is having an exponential of minus, and this is the exponential of plus. Always that will show up whenever this is also sometimes called the inverse Fourier transform. You have a function, these are its components, but if you know its components, you can know the function. So what are we going to do with this? We want to start solving partial differential equations. So the goal will be, or the general strategy is that in a space, like for example, in f of phi might be very hard to solve. You go to a space where this differential equation becomes algebraic. So you solve for f of m, which will be very easy. You don't have to solve differential equations for that. But then you have to invert it back. And usually that might be the harder part. The differential equations became easy. But now when you invert back, that might become harder. So somewhere you have to pay the price, but if you are lucky, then you can invert it also. We will see how whenever we have certain symmetries, things will become simple. Whenever there is a translation symmetry, Fourier transforms are useful. Whenever there is a spherical symmetry, we will use spherical harmonics and Bessel functions. That will be right. So there is one thing we restricted here, and that is that m was discrete.
So this
Yes.
in the second last we then put something space and that reduced to make you forget them.
Tell that again? Or
If that reduced object space, then that reduced to
oh, what I was trying to say is that usually we have a differential equation for f of y. We are interested in a solution to a problem. Let's say you're doing electrodynamics and or electrostatics, and you're looking for the angular dependence in the potential, like electric potential. So you would like to do that f of y, and it will satisfy the Laplace. Right? That might be harder to do. Usually differential equations are hard. You do the Fourier transform, all the differential equations will become algebraic, like linear equations, and it will become very easy to solve. So you will be able to solve for f of m, which is in the Fourier space, right? It has the components of the function. So that's not sufficient. You have to come back. If you go to a space where you solve for all the components, but now you have to come back and give me the actual function. That coming back might be hard, but if you can do it, then that's a successful strategy you make. So that is usually the idea, at least that's how we will use it here, is that we will use Fourier transform and any transform, like next will be spherical harmonics. So Fourier transforms are for translation symmetry. When it is spherically symmetric, then you use another function. So always a function space, the idea is there are some eigenfunctions, expand the function in that, find the component. Instead of solving the differential equation, find the component and then come back. Like after you solve for it, come back. And so that will be it. So I'll highlight that strategy a little bit, and even in your homework also you will see that you will solve a differential equation and find the components of. But before that, this is a discrete Fourier transform. This is notice m is going from discretely. So Fourier continuous Fourier eigenfunction. So let's say continuous. Same idea, except that now, let's say k, so m becomes k, and it is less than plus infinity. It is greater than minus infinity. And instead of phi, now you have x, which is less than plus infinity and greater than minus infinity. And your eigenfunctions, Fourier eigenfunctions will be e raised to I kx. Here it was I m phi. So that's also something you will see this in quantum mechanics also. Whenever the variable is confined, phi is bounded, right? If phi is bounded, then you have a discrete eigenfunction. If x is not bounded, then it will be continuous, right? You might have seen this in quantum mechanics. If you have a system that is bounded, the eigenvalues will be discrete. If it is not bounded, eigenvalues will be continuous. They are called scattering eigenstates and bound eigenstates in quantum mechanics. So that's the same idea. This generalizes now to completeness relation becomes instead of summation, you do integration, right? So say this is ek over q pi minus infinity to plus infinity e raised to I kx and I have to have e raised to minus I kx prime. That's what delta of x minus prime. Okay. That will be my completeness relation, and orthogonality will be do the same thing in x now, integrate over x, e raised to, this time x has to be the same and k will be different, so this will be minus I k is different, so k x, e raised to I k prime x. And that will be equal to again q pi. This will be delta of k minus k prime. Here it was delta mn, this was discrete. Conical delta becomes delta functions wherever things are continuous. Do the same idea here, that you take a function, multiply it by the completeness relation, and what you will get is, so instead of these two quantities, you will get f of x will be equal dk over q pi f tilde of k, and the Fourier transform would be and I chose my 2 pi in this position. Okay, so that will be mine. So these two will be the Fourier transform. You often say this is the f tilde k is the Fourier transform of f, or f tilde k is the Fourier component of f of x in this basis, in this eigenbasis. How do we do this? How do you do this to solve differential equations? Let me quickly solve that. Find the or solve a differential equation, let us say. And this also shows up in your homework. Let us say our differential equation is square over the x squared and say okay. That's a differential equation. What are the solutions to that?
E to the k naught x. K naught?
Yeah, I said k naught here.
Yeah, you k naught x.
Yeah, so this is k because I expect k itself to show up. And the suggestion is that if f was equal to exponential of plus or minus k0x. Right. Then let's see. First derivative of f is equal to plus or minus k naught times f of x itself, correct? This is f of x. For the second derivative of f, we'll bring down again at plus or minus k0 whole square of f, which is k0 square times f. So it satisfies. And once you can guess a solution, that is all that you need. It doesn't matter what procedure you use to do it, because always differential equations are unique solution. If you found it by guessing, that is the solution. It might be kind of linear combinations of the two solutions that you have. So that is, but let's try to do this in some other way. It is a simple case, but let's try to do this using Fourier transform. So let's or maybe, yeah, I complicate this a little bit, right? Yeah, let me complicate this a bit. Yeah, so this is a differential equation. Let's have, so this is a homogeneous differential equation. So homogeneous differential equation is, let me write that as second derivative of x squared minus k naught squared times f of x is equal to 0. It's homogeneous in the sense that it is 0 on the right hand side. Like there is no source for this differential equation. Make it inhomogeneous. And the simplest inhomogeneity you can bring is that there is a delta function. That's called a Green's function. So let's say this is equal to t squared over the x squared minus k naught squared. And now this is a different function. So let's say this is g of x. And to make it simple, I'll just write delta of x at 0. I could have written something else also. This is not a very generic Green's function, but this is what is called a Green's function whenever the right hand side, whenever the inhomogeneity is a delta function, you say it's a Green's function equation for this equation. But we will talk about Green's function in a lot more detail later. Let's say we want to solve this, right? And this is where Fourier transforms will become useful. So let's try to solve this. So we want to go to Fourier space, right? So we want to not work in g of x. We want to work in the components of g of x. That means we want a Fourier transform. So let's start from here, right? G of x. So our equation is e squared by bx squared minus x g of x is equal to delta of x. Expand g of x in Fourier components. This is minus and g tilde of k. Notice these are Fourier transform. If I can solve for g of k, I can invert it using Fourier transform to get g of x. Right? For example, if I can find this, then I can get my g of x by doing this integral. So what is g of k? And let me just, for completeness, write g of k also. It's minus infinity to plus infinity dx. Substitute g of x in the differential equation. So we have second derivative minus a0 square times g of x, I'll substitute this. Right, so I just substituted g of x, this expression, into the differential equation. I have to substitute something for delta x also, delta function. Delta function, remember from completeness relation, is this. Right. So if x prime is 0, this whole integral is what delta function is. Right? So I just have to set x prime equal to 0. So this is equal to integral again of bk over 2 pi minus infinity to plus infinity e raised to I k x. Is that clear? These are x dependent differentiations. This is an integral in k. This can enter the integral. Right. So I take the integral in. So this is equal minus infinity to plus infinity k over 2 pi. Where does this differential hit? Wherever it sees an x, the only place it sees the x is here. There is no x in here. Right. So it sees the x only in there. So I'll take it all the way to the right. Or doesn't matter. So this is equal to so this is g tilde of k. I'll move the g tilde to the left so that, and this is second derivative acting on e raised to I k x. Right? I move this and I'm planning to hit on this. G tilde k, and on the right side, I simply have minus infinity to plus infinity. Is that clear what I'm doing? I'm not doing any integral. I'm only using symbolically. I'm going in and out, but I'm not evaluating any integral. I'm only identifying what is what. Any questions on that? Clear? This derivative can act on this, and what will it give me? Minus k square, because each time it hits, it brings down an ik, right? So that's a good thing to remember. A poor man's Fourier transformation is wherever you see a derivative, replace it with ik. That's all you have to do. That's what Fourier transform does. A derivative becomes a variable. Okay. That's it. And that's how typically, I mean, even after 3 weeks down the line, you will get used to this so much that eventually this is all that is needed. But here I'm motivating that. So this derivative acts on that, and you get minus infinity to plus infinity ek over 2 pi. And this is g tilde of k. And when I act on this, this is minus k square. So this is minus k square minus k 0. Why is this a minus?
I squares.
I square, right? There are two k's it comes brings down. That's an I square is minus. Remember, these are exponential Fourier eigenfunctions. If you have a vector A, let's say A1 times I hat plus A2 times J hat is equal to B1 times I hat plus B2 times J hat. What can you say about A and B? if you have two vectors that satisfy this, what's the connection between A and B? A1 and B1? They're equal, correct? If two vectors are the same, their identical components has to be the same. Okay. Instead of I and J, we are talking about Fourier transform. These are Fourier eigenfunctions. These are functions. These are components of function. On the left-hand side, I have a function. On the right-hand side, I have a function. Its components have to be the same. Okay. What that means is that whatever is sitting here, that's a component. That has to equal, what is the component in here? 1, right? Very good. So that's 1. This has to equal to 1. Right? So that's because this is an infinite dimensional vector. So I learned that the tilde of K, this is Fourier transform it is, with a minus sign, K squared plus K0 squared has to be equal to 1. Right. So I solved for the Fourier transform. The components is equal to, notice this is what I mean by algebraic. This is a differential equation. Its Fourier transform is algebraic. There is no derivative. This is trivial to solve. Any of us can solve this. So this is minus 1 over, I solved it, correct? So I solved for the Fourier transform. I did not solve any differential equation. This is g of x. Now I know the Fourier transform of g of x without solving any differential equation. Is that clear what I mean by not solving a differential equation? But I still have not done the job, completed the job. I'm interested in g of x. So I have to do this integral. Right. So what is my g of x? Let's go back here. Think. So the actual solution will be g of x will be equal to minus infinity to plus infinity dk over 2 pi e raised to ikx, and g of k is minus of that, so it is minus 1 over k squared plus k naught squared, right? Do you know how to solve that integral? That's an exponential. Without the exponential, that's our time. Any ideas on how to do that integral?
Be like we said, as a contour general.
Very good, right? This has poles, right? We just have to find the poles and we are done. Right? We just have to find what the poles are, right? So where are the poles? Okay. So we have to now go to we have to build another contour, and then what are the poles? K squared is equal to plus or minus ik. So there is a pole here, there is a pole there. Do the upper C1 and C2 here. C1 is what we are interested in. C2 will go to 0. We have to at least choose our x so that it goes to 0, and we can solve for that. So now it is at least when x is greater than 0. So when x is greater than 0, right, we have g of x will be equal to residue of, like, this has to be complexified, right? So this 2 pi I times 1 over 2 pi, and then there is minus e raised to ikx, or minus, let's say minus 1 of k plus ik and k minus ik. So it is k plus ik, where k is evaluated at ik. So that's equal. 2 pi cancels out. So So this is minus I e raised to minus no k naught. So what does this help me? So k is so this is minus, right? So minus k naught x, and then this is 2ik naught, right? Or this is k naught. 2ik naught. So I will cancel out. I cancels out, and then this is minus. If x was less than 0, what do you do?
The control that has.
Contour that goes the opposite way. And then since the contour is going in the wrong direction, then there is a -1 coming in from there. The pole that its contribution is different. So for x less than 0, g of x would be equal to the minus sign is coming from the sign of the contour itself. That is 2 pi I, and there is 1 over 2 pi, and there is -1 e raised to I k x. Over this time, the pole is k minus I k, right? It's k minus I k naught, evaluated at k equal to minus I k. That's all. This requires more work, like we had done in contour integral. You have to make sure that the C2 integral really goes to 0. There is more work to that, but that will work out in this case. So 2 pi cancels out, minus plus. Right. So this is plus I e raised to minus, because cover again? Yeah, plus, yes, correct. And this is minus 2i k. Right, so this is equal to minus e raised to plus k naught x over 2 k naught. So the two solutions we have is g of x is equal to minus e raised to so this is k naught x over 2 k naught if x was less than 0, and it is minus of if x was greater than 0. Actually, these two can be written in a single form. This is just the same as writing minus magnitude of my k naught magnitude of x, right? So that's your first Green's function in this course. Right, you will see a lot of Green's functions. So that's a inhomogeneous differential equations are a lot more harder to solve than homogeneous differential equation. But we will learn that if you can solve the homogeneous differential equation, we can always find the inhomogeneous differential equation. But notice we solved this differential equation, again I emphasize, without really using the idea of derivative. We went to the Fourier space where it was algebraic, and then did an integral to do that. Which is, I mean, differential equation also involves a different integral, so it's not that great, but at least there is a strategy that go to a suitable function space, get the components, and then invert it. That will be our strategy. This is for Fourier transform. Every function space, you might have seen many functions, right? So these are the functions you will learn, right? Fourier eigenfunctions, then there are legendary eigenfunctions. Legendary is whenever you have azimuthal symmetry, whenever you have a cylindrical symmetry, that's what you would use. You can have spherical, this is called spherical harmonics. Then whenever there is spherical symmetry, you would instead of doing, whenever there is, whenever there is planar symmetry, you do Fourier. Whenever there is cylindrical, you do Legendre. Whenever there is spherical, you do spherical harmonic. And accordingly, there will be Bessel functions that will come in. You will have to talk about cylindrical Bessel functions and spherical Bessel functions. We will do all those things as much as possible. We are halfway into the semester, or not yet halfway. This is the 8th week. Usually there are 16 weeks and 15 weeks of classes. So we have about 8 weeks, and we will try to do as many differential equations as we can. And the main idea will be Green's functions. And these are the functions we will talk. But you might have been using Legendre and spherical harmonics in electrodynamics, correct? Or electricity and magnetism, right? There it is extensively used. But we will motivate that and make it formal. I'll stop here. Thank you.
All this related to quantum theory then.
Oh, good. I should have mentioned that. Notice earlier when we were doing, I said M is discrete. Like M was 0 plus or minus 1 and so on. And phi was continuous. If both are discrete, let's say phi is not continuous anymore and bounded, it is discrete. So let's say 0, 1, 2, 3. Then the eigenvalues will also be discrete and bounded. Okay. In that case, the best eigenfunctions to do is, we talked about roots of unity. Remember in complex numbers, we did roots of unity. That becomes the best eigenfunctions for it, and that's quantum Fourier transform. When you use the roots of unity as your eigenfunctions, then you have quantum Fourier transform. I constructed a homework problem, I think it was last year, which was based on that. So, yeah, just talk about it somewhere else and I'll tell you more.